Okay. How are y'all doing, everybody? Fine. There we go. Getting in that last little bit of a nap before we gotta go back on tour through some talks in the afternoon. My name is Paul. I'm going to talk to you about supercomputers. How many people are familiar with what nowadays is considered a supercomputer? People are there basically supercomputer players in the room? No? Fantastic. Great. Okay, because this is an intro talk, and I want it to reach the most people as an intro talk. So, without further ado, what I'm going to be talking about is a deep, shallow dip into the history of the supercomputer. Talk a little bit about the tools that surround supercomputing, and specifically the tools in Python. One particular tool, really. What I've done in terms of supercomputing, and the conclusions I've made from that. So let's get started with what is a supercomputer, and starting from way back when. So in the mid-1970s, Cray, Seymour Cray, came out with the Cray 1, which is a supercomputer, first of its kind. It operated at about 80, as you can see, megaflops, and we'll talk about what a megaflop is in a second. And the number of processors was really not super clear. Not like you can buy a computer today and be like, oh, there's 2 CPUs in that, or there's 2 cores in that. It wasn't quite clear. But 10 years later, they came out with the Cray 2, and it had 1.9 gigaflops and 8 processors. Assuming that the Cray 1 had 1 processor, you can see that there was, about 10 times of a jump, an order of magnitude jump in the number of processors, and an order of magnitude, maybe a little bit more, for jumping to processing power. So gigaflops and flops are floating point operations. And they're kind of the benchmark of choice for a supercomputer. They're not necessarily totally all-inclusive of a supercomputer's power, but it's the benchmark that you kind of use across pretty much every supercomputer out there, and that's why it's chosen. Where supercomputers really came into needing some type of messaging system, let me back up a little bit. This Cray 1 and Cray 2 were all one machine. So all the cores lived in one machine. And so there wasn't really any need for passing messages in between machines. It was just passing messages in between processors. And that's fairly easy. You can do that with Python's multiprocessing very easily. In 1993, you'll see there was a huge jump in time. And then a huge jump in number of nodes out there. So we went from having 1 machine to having 1,000 processors over 32 machines. So a compute node is like a machine, a computer out there, right? An actual box in a warehouse. And at this point, now we've gotten away from this ability to pass a message to another process or even another thread within the machine via just memory on the machine. Now we need some type of message passing protocol, specifically a message passing interface. And this is where MPI comes out. MPI is specifically a standard for passing messages between a bunch of different nodes. And this is where supercomputers really take on more of the nature that they are today. There's no real one big machine out there. It's more of a bunch of little machines. And that's the kind of supercomputer I'll be talking about and what I've done with it. For fun facts, there is the Earth simulator, and it's about 35 teraflops. That came out in 2002. And then the largest supercomputer today is the Tianhe 2, and it is about 33 petaflops, right? And it's got an extreme amount of nodes, 16,000 nodes. That's located in China, and you know what? I don't have my notes here. See if I can. Oh, there we go. You can see all those speaker notes, can't you? Or no, you can't see anything. Okay, well, going without help here. No notes. Fly a seat of my pants. It's let's see, where did I leave off? It's located in China, and there's not
there's stuff on the horizon, but for right now, that's the biggest thing. Using MPI and using this scale of number of compute nodes. So let's move on. There's basically two different types of supercomputers out there. There's the grid compute cluster. Grid computing style is where you've got a bunch of machines diversely located all over the planet, and they chip in effort whenever they can. Then there's the cluster style computer, which is like the Tianha 2 and the other supercomputers I mentioned out there, where they're all in one semi-decentralized location, all linked up via something like InfiniBand or something really powerful pipes connecting these nodes, and they crunch on numbers as hard as and fast as they can. It's not, oh, I'm a node, I'm going to take some work up when I can get to it. It's, I'm a node, use me immediately. I'm here to just work on your processing job that you hand out. So let's talk about communication. With all these 16,000 different nodes, how do I get a message from my core job, or my core machine doing this job, to all the other nodes? So we break this up into pi analogies, which is the most delicious of the analogies, and Leo references. We already have the pi. The pi is the job that needs to be done. We already know how we're going to get that job done. That's what we're going to feed it to Leo, right? The real task that we need to solve is, and we even have enough people to split up that pie, because Guido's not going to eat a whole pie himself. He's got to get some help to do it. So the job is really, how do we disperse this job into chunks and pass these messages along? So enter MPI. Let's go into details about that. Again, it's just a message passing system. It's written in C with a standard MPI CH2 is written in C. And at the base level, it's just chopping up a job, like the requirements that, the callables that need to be called, and the arguments to those callables, and serializing those in some way, and passing it through the pipe. So this is how you execute a job with MPI. Once compiled, you have an executable called MPI exec, and you pass a number of nodes. Say if you want 1,000 nodes working on this, and nodes in this sense is a little bit different than nodes that I've been talking about before. Nodes in this sense is more like cores, CPUs. And then you pass the number of hosts that you want, and specifically the location of those hosts, followed by a program. Most of the time, you're not writing out the total on a string. You're usually using some type of schedule like Sun Grid Engine or Torque or Portable Batch System, which takes care of knowing where those hosts are, communicating to the hosts, passing on the job. And all you need to really worry about is writing that program in such a way that it can be executed by a bunch of different hosts at the same time. This is where things get interesting, is your program is no longer sitting on one machine being executed on a bunch of different processes. Like I said, it's on a bunch of different machines being executed at the same time. So, how does a program like that look? Yeah. You have to specify whether or not you are a core node that's going to be spoken to, or you're a node, a worker node, that's going to do some work and pass work back to if you're doing this type of architecture of a job tree, where you have one core node giving out bits and pieces of a job to different workers. In Python, and we're jumping into MPI 4 quickly, MPI 4 Pi is just a wrapper around MPI in Python. You'll ask for some communication object, you'll get the rank. The rank is kind of like, which host am I? Which node am I? And they're just sequentially numbered. So if you passed in a bunch of different nodes, if your -10 parameter was 3, well then the first worker job is going to be 0, and it goes up from there. So if your rank is 0, you're going to possibly do some job of
creating some data and sending it out to the worker, or vice versa. And if your rank is 1, then you're going to consume that and maybe do some work on data, maybe pass it right on back to the core machine, or the rank 0 process. So how have I used it? Pretty much in the exact same way, except reverse from that other slide. I had a bunch of different worker nodes that are going to do some calculations for me. I'm going to pass in arguments and parameters so that they do the job differently depending on what rank number they have. And then they're going to pass back that information to the core machine where it does some reduction on that data. Inside calculate conservation, I'm calling com.send. So I'm sending data back to this core machine. Again, with that. So what kind of data was I working on, or what was the job? So I'm a web developer by day, and by night I like to do bioinformatics. I had no experience in bioinformatics, so I was at, but I still wanted to get involved. I was at one of New York City Python's meetup events, and it was just a meet and greet, get connected with other people in the industry. And there was this physicist that just politely came up and he was like, "Hey, yeah, you're working on blah, 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 blah. Yeah, my girlfriend likes doing biology. She's a biologist, and she likes working with the supercomputer she has access to. Maybe you guys could work together." And of course, at that second, I was like, "Absolutely. Who are you? Just sign me up, right?" Turns out she's working with microRNA. So if you are not familiar with microRNA and how our cells talk to each other, our cells excrete these little tiny bubbles of phospholipid bilayer, these vesicles. And inside the vesicles, there's microRNA. This microRNA can act as a signal to not only the cell that sent it, but other cells around, right? And we want to look at, and she really wants to look at, what's the composition of the microRNA compared to in the vesicle, compared to the composition of the microRNA inside the cell itself. And so she's sending out this data to get back these streams of microRNA. And this is exactly what comes out of the Illumina machine. Illumina is just a sequencer. And this is specifically dicer mice. It's a very common strain. I forget exactly which exact serial number. I never wrote it down of dicer mice this is, but this is mice RNA. And so I've got to go through and look at the second row of data. The first row is metadata. Second row is actual RNA. Third row is a plus sign, just because it's fun to put in plus signs everywhere, right? And then the last line is a quality line for your RNA. And that RNA actually is this line that you're looking at is really more DNA than RNA. Okay. What was the job that had to be done on this data? We had to take a look at this second line of each of these 4-line chunks and go, for an NMER, which is 6 or maybe 7 nucleotides long, how many different permutations of that could there possibly be? And how many times do I see each individual permutation? And this is a pretty standard job for something like counter in Python, right? But it's a little bit big when we were talking about NMERs that are 7 nucleotides long. That's somewhere around 16,000 different possibilities. And you're talking about these types of files, which can get to be 2 gigabytes big even, which is not big, but still you're talking about a hefty amount of data to expect to be popped out, answers to be popped out like that. So, despite me having a lot of interest in doing this type of programming, I didn't have a lot of time. So when I was tasked with it, I wanted to impress this biologist, and I wanted to get her an answer the next day, especially since you have access to a supercomputer. You want to start using it right away. Right? So I wrote up immediately the first thing that I could think of to solve this problem, and that job is for each one of these possible permutations, go through all those lines of files and see how many times you see the permutation, right? Now, you guys can't see it. There's a glaring problem right here, right? CS101, what's the glaring, maybe not problem, but inefficiency? Q&A. Yeah, we got 3 nested loops, right? Already this isn't looking good, but at 2 a.m. it looks fantastic, right? So I went ahead and, I shipped this off to the supercomputer. I was like, all right, I'm feeling great. And I knew it was bad, but it was a certain amount of bravado of, I've got a supercomputer behind me. I don't need to worry about writing good code. Right? Let me just let me put in an extra few for loops that just iterate over tuples of nothing, right? Actually, nuns or something. A tuple of nothing would do absolutely nothing. But I was very cocky. Immediately, I started to hit walls. I can only have that supercomputer for, not the whole supercomputer, of course, but my jobs can only last a day's worth of wall clock time. So it's literally like, my job can only last an hour in hard time. And in terms of processing time, it's taking several days to get this job done. That's ridiculous. And not only that, but we wanted to expand on the amount of data that we were working with. We're working with mice DNA now, right? We want to be working possibly with human data later on, and that's going to get longer. MicroRNA still only gets so long, but the amount of data we want to go through is bigger. So we already I knew that this wasn't going to be a feasible style of coding to maintain. So refactor was clearly needed. I jumped in after I realized that jobs were getting killed because they were taking too long. I jumped in and started to think about ways that I could refactor. Going back to Python office hours, so in New York we have Python office hours. We can come in and just work on whatever your project is for the day, ask questions if you have them, or maybe just sit and chill and work on the problem all along. Eventually, a friend of mine, James Powell, was there, and he said, why don't you re-encode the problem? Don't think about trying to solve the problem the way you typically are, but maybe re-encode the problem such that the answer is triggered once you've re-encoded the problem. Well, what I tried to think through and what I came up with is instead of going through or finding all possible permutations of this ATGC sequence, and then taking each one of those and going through the entire file and searching for it, instead, just go through the file and find chop it up by 7, overlapping 7 nucleotide pieces, and just count those all up. And of course, that's faster, and that gets me the numbers that I was looking for, so it's of course a viable solution. That solution, that algorithm, took 2 minutes to run on my laptop locally for the same data that took multiple days on a supercomputer. Ouch, right? Once that happens, you get for a certain second this fluttering of like, yeah, I kicked ass. And then you're like, yeah, but I wrote the stuff that was before it. And you're like, yeah. Don't get too confident too fast, Paul. So, very happy with what I did. I went out for the biologist. Okay, I can get you answers. I can get them faster. But I sat back and I tried to reflect more on this, and I decided this is what I want my talk and my point to be about. Is that supercomputing does not compensate for bad programming. And in a lot of ways, we are hitting the same walls that good programmers or plain programmers were hitting 30 years ago with machines that were, thousandth of the power of our MacBooks. We need to continuously pay attention to that algorithm. And for me, coming from a startup world where it's just ship it, that's really not going to be enough moving forward. We want to be writing good software. Of course, we need to be using good algorithms. This is all known. But
it can escape us. It can quickly escape us when we are trying to ship code. For another fun fact, just so you guys know, our laptops are about 10 gigaflops, right? And the largest supercomputer in the world operates at about, what was it? 35 petaflops, something like that. Yeah, wow. Cool. So I want to thank Cornell for letting me use their supercomputer to do this and playing other fun things like snakes and ladders. Just for learning how to work the supercomputer and program snakes and ladders on the supercomputer. Oliver Elementum's lab and Elisa, the biologist I work with. So I know that wasn't a deep dive into how to use NPI for Pi on a supercomputer. I'd like to open it up for questions now, and whatever they may be. Yeah.
I wonder if you use MapReduce frameworks, for example, and how they compare to
Yeah. I haven't used Hadoop, one, because it just wasn't available to me. The supercomputer was basically handed to me on a platter. I was like, yeah, sure, I'll take that supercomputer. But yeah, I definitely could see it being a really good solution for this type of a problem. I don't see us building, we're in the process of building out a framework for doing this type of bioinformatic crunching that she wants done. We're not building it out for Hadoop. Hadoop's a big old box. And so, well,
that's like a tool that, not mine, but
yeah.
Mr. Job is a Python wrapper around
Hadoop.
Yeah, and I have I'm not
Mr. Job.
pull off of it here, but Mr. Job makes doing sort of accessible.
I'll take a look. Yeah. Thank you. Always willing to give suggestions. That's what we're all here for, right? Yeah. Cool. Question. Is that white record?
Yeah.
Hey. Yeah, that's a great question. Here's where you're going to use MPI. From my limited experience, let me also preface that I'm not trying to hit myself down too much. I have spent about a year working on this in my free time, but I'm not the industry expert. From my experience, if you have a supercomputer, you're going to need some way to talk code between those nodes, and that is MPI or some other framework of the sort. If you're going to spin up stuff on like AWS, where there's machines, the machines have already kind of a built-in messaging system that works with you, use that. Basically, what do you have available to you? And on a lot of supercomputers, which schools bought, back in the 90s when the supercomputer world was hot, and they're still buying them, but less so like they were before, then you use what you have on the supercomputer rather than use what you can buy for minutes at a time in AWS and use their types. That sort of answer your question? And then when it comes to data, I see you, Steve. When it comes to big data, big data is pretty much, I feel comfortable saying big data is anything over what comfortably fits in your machine, right? So for me, in memory, anything that's in that multiple tens of gigabytes, that's big data, and that needs some space to itself. So I'm going to leave it at that.
I would advise someone to get started when they come across a problem they need to solve. I would suggest they get started figuring out how they can work.
Oh yeah, I would say it's hard. It's really hard to bootstrap yourself with a machine. It's only one machine, right? Because what is a supercomputer nowadays? I didn't really get this home enough. It's a bunch of different little machines working together, and it's hard to have that at home. I would say go ahead and write it. If you're looking at the docs, go ahead and write it. Like the doc suggests, NPI, Pi, it has really good docs. and then put it up somewhere and have somebody else that's doing this kind of stuff take a look at it. That's actually my best critique, or my best suggestion. Because without the machine to run it and debug it, you're really not playing with it in the environment. You did not get those bugs. Oh, I'm sorry. If I didn't, it's floating point operations per second. And I did say I'd go over that. I lost my notes, so I forgot to mention it. My apologies. Floating point operations per second is a metric that's produced by a program. The program itself is made by Linpack, or maybe the Linpack is the software itself. I'm not quite sure. But anyway, it looks at how many floating point operations this machine can do per second, right? That's not, it's great for just giving a, hey, here's a stamp of grade A meat or grade B meat, right, when it comes to machine. But honestly, there's a lot of variation in all the different sizes of grade A meat that we have, right? Are we vegetarian or vegan? Fantastic. Okay, so you know what I'm talking about. So it's your machine is not constantly, every node in your supercomputer isn't constantly doing floating point operations per second. So although that metric, might be super high, it doesn't necessarily mean that your job that does 2 floating point operations per second will operate above some machine that has a lower floating flop. Yeah, question in the back. In math? Good. Neither do I. Cool. Yeah. Yeah. Yeah, I'd say if you're interested and have the time, go ahead and go for it. Who cares what all those other people say? Go for that class. Always learn more. But yeah, if you're strapped on time, maybe going over some of those. I don't know. Do you have a background in CS in school? I also don't. I don't mean to put you on the spot. Did you take the CS class? Yeah, so I took a few online and specifically just focused on the algorithms portions of those courses, and that significantly helped me more, right? I can talk to you, in person about one particular class, which is very intro class, and it gave me a wonderful introduction to algorithms. Now, beyond noticing that you're using three for loops, nested for loops, there's not a whole lot of algorithm study that you can really apply, right? There's people, but that's their whole job, is just go out there and search for that new algorithm that's coming out. So there's a lot of depth that you can go into algorithms, and it's just maybe not really worth it for your use case. So I would say get yourself informed on those basic ones, and the basic no-nos to stay away from, and that will get you 80% of it. Cool. Oh, I'm being told to kill. So, thank you so much for having me, and we'll see you out there.